All right. Hi, everyone. Thank you for coming to our session. This is the first talk that our team has done about the work that we have been focusing at Lyft for the past few months. So Mike and I are really excited to be here and sharing this progress with you. In this talk, we want to introduce you to Envoy Mobile, which is a child project of the Envoy ecosystem. And it is building Envoy as a multi-platform mobile networking library. With Envoy Mobile, we want to push the edge of your network topology to include your mobile clients so that these mobile clients become another node in your network, part of the mesh. So we want to take you through this story in 4 parts. The first part is sharing with you the motivation for why we want to bring Envoy to mobile. As any other project, it's a big engineering effort, and so we want to justify that effort with all of you. Next, we will dive deep into the internals of Envoy Mobile and what it took to bring Envoy into our mobile clients. Then we want to share where the library is right now, both as an open source project and also in its integration with the Lyft app. And lastly, we want to share some of the exciting roadmap items that we have planned ahead. So let's begin with the motivation of building this project. As all of you might know, Envoy is a network proxy that is extremely flexible. So with Envoy, a lot of companies, Lyft included, have moved into this type of topology where Envoy is dealing with network traffic all the way through and through, from the edge of the infrastructure into the service mesh, and even fronting third-party services and data storage primitives. Envoy has done a great deal in making the network more reliable server-side by having this universal network primitive that is configurable, extensible, reliable, and observable. We have really made the network transparent to our server engineers. And more importantly, because Envoy has best-in-class observability, when problems actually happening in the network, we have made it increasingly easy to debug. However, our premise with this project is that 3 nines server-side are actually meaningless if the application flows that users interact with in mobile applications are actually only successful a fraction of the time. So we believe that with Envoy Mobile, we can extend all the benefits that we have brought server-side with Envoy to our mobile clients. But that vision requires a paradigm shift, because traditionally, we've thought of mobile clients as independent from the backend mesh. And we've built a unique solution for what we have thought is a unique space. So we really can say that Envoy has become this true universal network primitive if all the network flows for our mobile platforms start and end in the mobile client, which is the only hub that Envoy is not running in. So we are proposing that we don't need to treat the mobile client any differently. We can have our clients become another node in the network, another part of this homogeneous mesh. The problem is that current solutions are platform-specific, both for iOS and Android. So we really can't have this true networking substrate that is all homogenized. In other words, there's no open source solution that is giving us this universal network primitive. And this is where we believe that Envoy Mobile fits. Because with Envoy Mobile in the client and Envoy server-side, we have this true standardization of our networking substrate. It's similar to what Kubernetes has done for container orchestration. And so we want Envoy to do the same thing with standardizing the network. So why do we believe that standardization is important between the mobile client and the backend infrastructure? Well, we think it's important by largely similar reasons of why standardization in the backend was useful. So first of all, we have this tenet of write once and deploy everywhere. By having this universal network substrate, we can embark on projects that would have otherwise been prohibitive due to the engineering effort of implementing these solutions in 3 different platforms, iOS, Android, and the backend. With a true universal network primitive, we can invest our resources on that one networking stack and deploy it everywhere. Second, we can share common tooling for common problems. So for example, by emitting the same metrics everywhere in our network topology, all the way from the clients to the edge to the mesh, we can share the same infrastructure and the same visualization tools to give a clear flow of how our network traffic is flowing. And lastly, by having this common network substrate, then we can homogenize the behavior and the reliability of our network. And by doing this, we're really reducing the cognitive load of our engineers that have to operate this network, because all the guarantees are the same end to end.
All of this sounded really compelling to us. We were still struggling to solve a set of problems on our mobile devices, which we had solved elegantly and consistently across our back-end infrastructure. But we were still left with the question, was this even going to be possible? Envoy runs in the back end, of course, as a server in a dedicated multi-threaded process. And you can't do that on a client. There's no such thing as a sidecar proxy that can run on iOS or on Android. We needed some way to actually run Envoy inside an app, the only kind of process that's allowed to run on mobile devices. A lot of our initial effort was simply invested in answering this question. We worked to actually build Envoy within an application as a harness and just get the server started, just get it running and see that we could run it on iOS, on Android, with the different platforms, OSs, and architectures. We knew we wanted Envoy Mobile's core to be Envoy. And once we'd answered that question, we were finally able to actually start working on developing not a server which would run on the client, but an actual library, something that would run as an engine in the client. We used Bazel as our build system, not only because it's Envoy's build system and offers numerous advantages in terms of incremental builds and parallelizable builds, but also because it has great multi-platform support. We knew this project was going to require us to build code in Swift, Kotlin, Java, Objective-C, C, because we wanted the actual core of the library to be platform agnostic and share as much code as possible, and C provided that common bridging layer. And finally, the actual code that runs Envoy and works with Envoy's native types and interfaces. This kind of caused our library to form a 3-layered architecture. On the right, we actually have Envoy itself as one of our Bazel targets, and that really forms the core of the library. It does all the heavy lifting. Then we have code that interacts with Envoy, and then the blue layer in the middle is actually our bridge code. It's the code which actually allows the platforms to call down into Envoy, Envoy to call back up to the platforms, without us actually needing to embed any sort of platform-specific logic in the code that works directly with Envoy. It also allows us to potentially support other languages in the future as well, other environments. And finally, we knew we wanted application developers not to need to know a lot about Envoy in order to realize the benefits of this library. We want them interacting with interfaces with which they're comfortable, using mechanisms with which they're comfortable. And so we have platform-specific code to provide flexible bindings into the library, and that allows platform developers to use the patterns they're familiar with. Again, this sort of forms 3 different layers in our library. We have the platform code written using high-level platform constructs. We have our bridge code, which bridges between the two and provides a platform-agnostic layer. And finally, we have the code which actually works directly with Envoy and leverages its native types. Still, this doesn't answer the question of how do we take code that was written to run in a dedicated server and actually run it on a mobile device in an application and as a library? How do we take something that was meant to be a server and make it an engine? To start to answer this, it's helpful also to look at the actual context under which code can run. First, we have application threads. The application threads are threads that are owned by the actual app. They're started by the app. They're the threads where other application code runs. And ultimately, it's the code which will eventually need to call down into Envoy to issue requests in order for the library to be usable. We made the decision to have our library be single-threaded just to allow it to be more streamlined and operate with more predictable patterns on the device itself. Fortunately for us, Envoy itself actually is largely single-threaded code. Despite the fact that Envoy is a multi-threaded library, or multi-threaded server, most code has been written to assume it runs under a single-threaded context. There's very little synchronization, very little shared state. Instead, explicit mechanisms are used to actually communicate across threads. And finally, we have callback threads. These are potentially the same threads as the application threads, but importantly, they're provided by the application. We wanted users to be able to specify how they wanted callbacks to fire, where the code will run. If we take these 3 layers and we overlay them over the 3 threading contexts, we can actually walk through what it looks like for a request to traverse Envoy Mobile and explore a little bit of its architecture and how we solved this paradigm shift. When a client goes to actually use Envoy Mobile, first they create a client, which will form their primary interface into the library. Under the hood, the client creates an Envoy engine. That engine is then actually responsible for starting Envoy's runner thread, the thread which will become Envoy's main thread, and is in fact very similar to Envoy's main thread. They are the same as far as Envoy is concerned. The one notable difference is that the event loop, which drives Envoy, runs under a very different pattern in Envoy Mobile. Instead of running almost constantly, doing bookkeeping and management of the server, instead it's primarily reactive. It wakes up in response to I/O events and platform calls, and that's about it, only rarely for other work. Now, in server-side Envoy, in addition to Envoy's main thread, we have worker threads. When Envoy is functioning as a proxy, when a request comes in, a listener will take a request and assign it a dedicated thread, which it will stay on for the entire lifetime of that request. When that worker thread needs to communicate with the Envoy's main thread, it will use an event dispatcher that's dedicated to the main thread, and that event dispatcher is backed by a low-level event library like libevent. Additionally, worker threads will sometimes need to perform asynchronous work, like issuing a request out to the internet that's a side channel from the actual main proxying pipeline. This could be to perform auth with a different server, or do rate limiting. It uses a construct called an async client to do this. We took an event dispatcher and an async client and used these to form the core of our alpha release direct API into Envoy. Basically, these are the code paths that we use to actually get code into Envoy running through it once it's been initialized. Now, when it's time for a client to actually issue a request, it will do so by means of creating an HTTP stream at the bridge layer. We have these platform high-level types. We have NS data representing buffers or potentially byte buffers from Java, and we need to convert them into something that Envoy can understand. This is the work that our bridge layer does. It converts them into C types that can be mapped directly into Envoy native types. We have another issue here, however, and that's that the memory we're getting from the platform, which is essential for both the headers and the actual bodies of requests, is owned by the application. It's being managed on iOS by ARC, by automatic reference counting. It's being managed on Android by the JVM and the garbage collector. And Envoy knows nothing about this, and we didn't want Envoy to know anything about this. This is another case where we've been able to actually leverage a useful pattern already in place in Envoy to actually solve this problem. Envoy maintains an abstraction around buffers. Rather than working with direct memory addresses and lengths of the buffers, instead, a buffer is an abstraction around buffer fragments. Buffer fragments know how to retrieve the memory when it's time for I/O to be performed, and they know how to release that memory when Envoy is actually done with I/O, but they don't really expose anything else. We've extended this concept of buffer fragments and actually mapped it back up to the platform layer. So we're able to represent this platform memory in a type that Envoy understands directly. When Envoy is done with the memory, we then signal back up to ARC, or the Java garbage collector, that Envoy is done with it. Envoy doesn't deallocate the memory. We don't know if the platform's done with it, but it also doesn't need to know. The platform can resume its normal handling of the memory and release it if necessary, or maintain it if necessary. This is an elegant pattern which we've been able to extend and actually avoids a lot of complexity in passing this memory. Notably, it also avoids us needing to copy buffers unnecessarily. We can use the same memory that was passed to us from the platform and pass it all the way down to the socket that's being written in Envoy. Here you can actually see, just briefly, what that struct looks like at the bridge layer, including the callback that Envoy uses to release that memory in a form where it's entirely agnostic of the platform. Once we've converted the types, we're ready to actually pass them into Envoy. We use the event dispatcher to get it onto the main thread. The async client issues the request, and it goes out into the internet. Importantly, this is actually the same code path that Envoy is using on the server to send requests to the internet. This means we get the same stats. We have the same points to actually work with it. It's truly running on the same code. It's the same platform, despite the fact that it came from platform-specific code as opposed to a request that Envoy is proxying. Once we get a response or get an error, as the case may be, it's time to actually surface that information back up to the platform. Again, first we need to traverse the bridge layer. We need to send this up from Envoy without needing to tie platform-specific notions in the code that works with Envoy. We want this to be portable. So these callbacks are, at this point, simply function pointers. We also don't want platform code actually blocking Envoy's main thread, since it does have important work to do when it wakes up. So we also need to get things on the callback threads. We achieve this by means of dispatchers that are provided by the platform and unique to the platform. So on iOS, we are talking about Grand Central Dispatch and dispatch queues. On Android, we're talking about executors and runnables. We chose patterns that could be extended to work with other models of concurrency people are using, but again, which would be familiar to application developers. Now, we still have a problem because we don't want Envoy or even the bridge layer to really understand anything about the platforms we're calling into. And so we've used an old C pattern to allow the platform to pass in state, which neither Envoy nor the bridge layer knows about, via a type-erased context parameter. This context parameter is specified by the platform and basically contains everything the platform needs to know when the callback that is provided is also called in order to take a static C function pointer with no state and turn it into a platform lambda which can run and be dispatched using that platform's own mechanism. It essentially hydrates the lambda from the C primitive. We've also deliberately made the choice to keep these paths unsynchronized from each other. This is a pattern which, again, we take from Envoy. Envoy's code is mostly single-threaded and doesn't share state. Similarly, we knew that code in the application where the request is issued might be very far, might be remote from where the actual response is being handled. So to avoid a lot of bookkeeping and tracking that would be necessary, instead we provide contracts around when functions are called and when callbacks are issued so that the state can be largely unsynchronized. Really, the only exception to this is cancellation. We dispatch this as an interrupt in both directions, again, providing strong contractual guarantees, and so it forms the only actual atomic shared state. And that's a high-level step through of what the architecture of Envoy Mobile looks like today and how we're able to actually work directly with high-level platform code, but still call into Envoy's internals for all the important work that's done with HTTP.
Well, thank you for that excellent deep dive, Mike. So with all that built out, let's take a look at where the library is today, both as an open source project, but also in its integration with Lyft. A few weeks ago, we released version 0.2 of the library, which we consider to be in alpha state, ready for people to experiment with. While the API might change very slightly, we believe that the design decisions that we made are sound and foundational to the library. Additionally, and perhaps more importantly, for a little over a month now, we actually have integrated Envoy Mobile into the Lyft app, and we have released it to our alpha release. This actually is a picture of our team taking the first Lyft ride in history, where all the network requests were dispatched through Envoy Mobile. We actually went and grabbed some donuts. So let's take a look at how we integrated Envoy Mobile into the Lyft app. And this starts with how Lyft does public APIs. At Lyft, we have taken a model-based approach to our APIs. What this means is that when an engineer wants to create a new public-facing API, all they have to care about is writing the model, and we have chosen Protobuf to do that. After that, our generation pipelines actually generate clients in all of the supported languages at Lyft, both for our mobile clients, but also for our backend services. If you're interested in learning more about our model-based APIs, I'd encourage you to check out a blog post and a talk that my coworker, Michael Rubello, will put up in the Lyft engineering blog later this year. After the generator has generated this clients for us, we've actually gone a step further in our mobile clients, and we pre-compile these files into modules for iOS and for Android. We do this in order to reduce compilation time for our mobile clients, but also to better organize our APIs and manage our dependencies. And what this abstraction really has done for us is it has given us a way to transparently shift implementation details about these clients without interrupting or having to ask our client engineers to upgrade their libraries. More specifically, what this means for Envoy Mobile is that by having this abstraction layer, we can transparently remove classic networking libraries like NSURL session for iOS and OKHTTP for Android, and instead put in Envoy Mobile in those generated clients. So replacing those API calls for API calls that we exposed in the platform layer that Mike was talking about. So let's take a look at those platform APIs. And something that I want to highlight here is that we have made it a goal of the project to actually have nearly identical parity between the ergonomics of using the platform API in iOS and in Android. So while here up top you see Swift and Kotlin, moving forward I'm just going to show the Swift code, but you can assume that the Kotlin code looks nearly identical. So the first thing that you do is you build an Envoy client, and this is the object that is actually instantiating and managing the lifecycle of the engine underneath, and it's also the interface that is used in order to make network calls. When you build the Envoy client, we also expose configuration points at this level. For example, you can change the logging of the engine or even the stats flushing interval. Then you can build a request with the request builder and the API path that you want to hit. At this point, we have also exposed ways to add custom headers and also, and more importantly, to change the behavior that the network behavior that this request will have. So for example, here you can see that we can attach retry policies to this request. I want to be very specific here and highlight that this retry policies actually map to behavior that Envoy itself conducts. So it's the same networking code paths that handle retry policies in the backend. So lastly, you build a response handler, and this is the object that is going to receive those callbacks back from the engine that Mike was describing. So for example, when headers come back on the stream, or when data comes back on the stream, these are the handlers that are going to deal with that. To wrap it all up, you submit the request and response handler into the engine, and then the engine gives us a way to interact with the open stream, for example, by sending data and until you close it. So while we have integrated Envoy Mobile at Lyft based on these model-based APIs, we actually want to make the library an easy drop-in replacement for all sorts of patterns in mobile clients. So for example, we want to expose bindings for the classic networking libraries like NSURL session in iOS and OKHTTP in Android. So we started this project with the premise that mobile clients were really primed to receive the benefits of Envoy that we have seen in backend services. With the alpha release of Envoy Mobile at Lyft, we embarked on this journey, and we started with observability. So as you may know, Envoy has best-in-class observability. For example, it flushes nearly hundreds of time series metrics that have become really essential for Lyft engineers to monitor the network. Well, now that Envoy Mobile is running in our mobile clients, we have access to those same metrics coming from the mobile clients. So here the goal is that engineers are able to really monitor and observe the network end to end using the same tooling and the same concepts. Metrics is one of the places where we have already started to receive dividends from building Envoy Mobile on top of the Envoy core, because Envoy's high extensibility has given us access to different stats sinks. And specifically, it gave us access to the metrics service, which is a way to get Envoy metrics out of Envoy Mobile using protobuf and gRPC. So we built a very small gRPC server that just receives those metrics and then emits them to our already existing observability infrastructure. And what this really allows, and this is the very powerful part, is it allows us to build dashboards like this, where up at the top you see metrics coming from our mobile clients, in this case, the total number of upstream requests, and then complementary at the bottom, you see the same metrics at the edge of our infrastructure. I really want to highlight how powerful this is. It's giving us insight that we didn't have before coming out of the mobile clients. And it's giving us a way to really monitor the network all the way end to end using the same constructs. This is really the first of many examples of the possibilities that we're unlocking by having Envoy Mobile in our mobile clients.
As Jose shared, we really feel we're just beginning to unlock the potential of Envoy Mobile. We sort of have table stakes at this point. We have a networking library. It actually works like the other networking libraries that are available. But Envoy is so much more than just a networking library, and we feel that a great deal of that translates to the clients. In the very near future, we're going to use this as our platform to implement QUIC and HTTP3 on our mobile clients. Having gone through this sort of thing before, it's much harder doing this on both the back end and on an Android device and on an iOS device than it is working with a single common stack without discrepancies and vagaries that go into multiple different implementations. Additionally, working on next-gen protocols was previously something that was really out of the reach of most organizations. Someone like Google or Apple could do it, sure. They have huge resources in terms of engineering. But again, you have to build this for different platforms and ensure interop between them, and that's an immense undertaking. With Envoy Mobile, you can build a single stack and run that single stack, reason about that single stack, and actually be able to deploy something that's consistent. Envoy is also an incredibly extensible platform. By means of its filter chain, you can introduce almost any logic into request processing. We see a lot of opportunity to leverage these filter chains on the clients, just like they've been leveraged on the back end. Some obvious early examples that, again, we plan to work on in the near future are auth. We see a single auth implementation as possible for OAuth on both the clients and the back end by virtue of an Envoy filter. Compression is another example. Sure, it's possible to get gzip support rolled out to your clients because everything supports it already. But say you want to experiment with Brotli, Google's new protocol for compression. That's something which, again, you can do by virtue of implementing it once and deploying it across your entire mesh, which includes your clients. Envoy already has intelligent network behavior. It selects connections, it selects hosts that are healthy, and rejects ones that aren't. We see this as something we can extend to clients, selecting cellular or Wi-Fi connections based on network conditions, falling back from IPv6 to IPv4 for networks that don't support it, or similarly, from QUIC and UDP-based protocols to TCP-based protocols when needed. Jose shared the model-based API that we use at Lyft, and we actually plan to expose support for this directly in Envoy Mobile, despite also supporting standard HTTP. With the model-based API, we see opportunities to actually annotate it. So you could actually annotate the schema of the model with the behavior you want it to face under different network conditions. Maybe you drop certain fields under the face of low bandwidth or poor connectivity. Maybe you mark the model as something that can be sent deferrable, or that Envoy can mock a success for when it's offline so that the application flow can continue. And Envoy transparently in the background could synchronize with the server later. Envoy is very configurable online. And again, we see this as something we can extend to the mobile clients. When you need to fail over, you could do it by virtue of Envoy configuration that's distributed via XDS, as opposed to actually needing to use server-side controls for it. Or when it comes time to roll out a new POP, rather than needing to roll out new clients with new DNS configuration, instead, you could do it via Envoy configuration. And even beyond mobile phones, Envoy Mobile is truly a cross-platform library. We're already exploring integration with Lyft's fleet of rentable transportation devices. We've considered IoT. We've also had interest from folks even just looking to use it as a replacement Python networking library, because at the end of the day, it is a high-performance C++ library under the hood. The C bindings there make this all possible. Envoy's success as a platform is largely because of its vibrant community that has contributed from open source across different disciplines and across different organizations. Envoy Mobile is also being developed completely in the open. It has been open source since even version 0.1, when we really just barely had a proof of concept. We'd like to welcome you all to join us in working on this platform. Let us know what your needs are, contribute to the library, and join us in revolutionizing mobile networking. Thank you.
We have 5 minutes for questions.
Okay.
Yeah, let's start here.
With Envoy in the data center, you have control over all the nodes that are connecting. Having this distributed and potentially exploited by somebody that is malicious, what concerns do you have in that area? Do you have any How have you approached that?
I mean, we definitely, it's something you have to be concerned about, right? So if you're talking about sending down dynamic configuration, or even potentially in the future, dynamically executed code, like via WebAssembly or Lua, which are supported by Envoy filters, that's something you have to be concerned about. Envoy, of course, does have mechanisms already in place for doing both encryption, via TLS, and also authentication, whether that be certs or another mechanism like OAuth. So you'd have to be careful about what you built and what you accepted in terms of configuration. Security is definitely something we're thinking about. We wouldn't actually include functionality in the library that could introduce arbitrary configurations or run arbitrary code without putting a lot of thought into it. That said, there are cases where Envoy Mobile can actually potentially make things even more secure just today. Envoy already has support for client-side certificates for TLS, for certificate pinning. You can do a great deal more configuration around what kinds of TLS connections you're willing to make under what circumstances with Envoy than you can out of the box with pretty much anything else out there. Just because, again, it's Envoy and it's what Envoy supports. So there's actually security wins, I think, even today. Granted, it's alpha software, so be careful, but there's at least the opportunity to realize some security wins today.
Hi, great talk. Do you know what the impact was on the CPU and the memory that this added to the app? Also, its impact on the download size?
Yeah, so early on, we established benchmarking for CPU, battery consumption, and the binary size. And it's something that we actually want to run every time we're cutting releases. We're running regression tests against those benchmarks to keep that in check.
Yeah, so actually we already have binary size in CI. So we're already tracking that because that's an item of concern for mobile applications. And we did early on see performance issues. That's part of why we retuned Envoy's main event loop. So it's much more relaxed now. Envoy is basically not doing work now unless there's networking happening. At this point, you'll see very little impact outside of maybe degenerate conditions.
Mm-hmm.
Yeah, I had the same question about app size and resource requirements. And also, what about the data usage? You said you're sending a lot more metrics, right? You're sending more metrics than before. So is that impacting data consumption a lot, or just?
It's a two-layer answer, I think. The first answer is right now we expose the ability to configure the frequency at which you're actually emitting metrics. Later on, we actually want to create interfaces where we can actually batch metrics and only flush them, for example, when the app is getting backgrounded or going to be killed. So we're only actually getting, emitting metrics when that's happening.
And it's configurable is the other part of that answer, right? Mm-hmm. So no matter what, if you want increased insight into what's happening, you're going to have to send something. And the best answer to that is I think we can try to send it as efficiently as possible and let whoever's using the library decide what they want to send and how often they want to send it.
Mm-hmm. Hey, awesome project. I like the initial announcement from Matt Klein on this.
Thank you.
Just wondering, you have Envoy Mobile and Envoy on the server side. Mm-hmm. Let's say my company decides to adopt this. What is the advantage that you guys, not right now, if not right now, or in future as well, in terms of connectivity? We use Istio. Also would like to say, stick to Istio for having Envoy as a sidecar. So that's the question. Basically, if I want to bring Envoy Mobile, just like Lyft would for their app, for any app in general, or even IoT going forwards, what is the advantage? I see, library and functionality and algorithm being similar and being shared, and maybe being more slimmed out for smaller, resources. But what is the benefits I would obtain being equal on either side, or having similar functionality on equal side, both sides, server and client?
So let me actually try to unpack that a little bit. That's okay. Of course, we see a lot of potential benefit to running Envoy. Are you asking about benefit to running Envoy Mobile as opposed to running Envoy as a sidecar in certain cases? Or are you just asking about the benefit of running Envoy Mobile as a network library in general, regardless potentially of even what you're running on the back end?
Okay. If I'm already running Envoy on the server side, I'm going to want to use Envoy Mobile, what benefits would I have, like to connect, to be able to use both in client and server?
So it was what's the benefits to using both? And we're going to have to do a brief answer and cut this off. I think we're out of time. But let's talk about it more after. Briefly, though, again, it's just if you're already used to running Envoy, you're realizing those same benefits. If you have dashboards driven by Envoy, you can drive them from your clients now. If you have configuration you're used to running for Envoy, you can configure your clients now. Extensions that you build for your backend can work in the clients where they make sense. So it's actually having that common layer everywhere. It's kind of why Envoy is great for the backend in the first place.
Thank you, gentlemen. Appreciate the talk. Please rate this on the schedule. And if you have further questions, please take the conversation out to the hallway as we have another talk moving in.
Yeah.
Thank you, everyone.
Thank you. We'll stick around, so if anyone has questions, we'll be out there.